In this lesson, we're going to learn how to build a confidence interval for proportions. We're going to finally start thinking about statistical inference, which is where we use data from a sample to make conclusions, which we call inferences, about the population. So what have we done in this course? Well, we've looked at different sampling methods, and we've looked at good sampling methods and biased sampling methods. So what we're going to be given is, a lot of times we only have a sample and some statistics about that sample. It's not typically feasible to know the parameters of the entire population. So we make conclusions about this sample and make an inference back to the entire population. There are two ways we do this. We do construct confidence intervals, and we're going to be eventually doing hypothesis testing. This video is going to begin our discussions about building these confidence intervals. We just finished talking about sampling distributions, and specifically when we're talking about a sampling distribution for a proportion, we said that our mean is equal to our true proportion, and then we calculated our standard deviation by doing our p-value times 1 minus p divided by our sample size. And what we were basing this on was knowing our true proportion of our population. But if you think about that, that's not always possible. You're not always going to know the true percent of, let's say, fish in the ocean that exceed, 5 inches in length. Okay, what proportion of the fish? Well, I don't know, but what I could do is take a sample of fish, find what percent are greater than 5 inches in length, and construct a confidence interval to capture the true proportion of all fish who exceed 5 inches in length. So as we build confidence intervals, the reason we do this is because we don't know our true proportion or our parameter, which leads me to this idea of standard error. We talk all the time about standard deviations when we're looking at the normal model, but if we are not given our true proportion or true population parameter, we use this idea of standard error. So what is standard error? It's just when the standard deviation of a statistic is estimated from the data, the result is called the standard error of the statistic. Think of it as the next best thing to standard deviation. We use it the same way as standard deviation, but when we are estimating it from a statistic, okay, so it's just an estimation using our p-hats, we're going to call it standard error from this point on. We are going to be building an interval, which we're calling a confidence interval, that captures the true proportion of our population. So our population proportion, known as a parameter. All right, so our confidence interval, to do this, well, again, we often don't know the true proportion, which is why we're building this interval, but we do know our sample proportion. So let's say that 60% of a random sample of students love Dunkin' Donuts mocha latte. Okay, so 60% love a mocha latte. But what proportion of the entire population really love mocha lattes from Dunkin' Donuts? So what I do is I recognize that my sample, I'm going to call that my point estimate, has a margin that I'm going to add on this way, and I'm going to subtract this way. I'm going to call that my margin of error. Okay, that I'm going to add on to get a range of values that captures my true proportion. The wider that interval is, the more confident I am that that interval captures my true proportion. The more narrow it is, I won't be as confident that I caught the true proportion. So if you look on your formula sheet, this formula is given. It says a confidence interval is equal to your statistic. Well, we're talking proportions, so that's my p-hat. That's also sometimes called your point estimate. Remember, p-hat estimates p, x bar estimates mu, and then it's adding and subtracting your margin of error. Okay, so I'll just write MOE for margin of error. And this margin of error is equal to our critical value times our standard error of our statistic. So our critical value, those are just your z-scores, okay? So how many standard deviations away? But of course, I've got to do something that's a little tricky here. I'm going to call it z-star. Why not just a z-score? Because I'm going to be using and I'm calling it z-star here because I'm using p hat to calculate it. All right, I don't know my true p, so I can't call it quite the same thing. It works the same way, we interpret it the same way, but it's going to be z-star in notation times the standard error of our statistic. Again, what is standard error? It's the next best thing to standard deviation, okay? I can't call it standard deviation because I'm not calculating it from my parameter. I'm using a statistic, which is an estimate, to calculate it. All right, so we're going to construct our confidence interval. As I was stating, the more confident I am that I'm capturing my true proportion, the wider my interval is. So this graphic here shows you some great things. This figure shows some different confidence intervals, okay? So between here and here, this red point would be our point estimate. The blue lines are representing your margin of error, okay? So we have all these different intervals here from 20 different random samples. And this green line is representing our true proportion, which of course we don't always know. Notice that most of our intervals here are capturing that green line, okay? I see some that don't. I see 1, 2, 3 right here that miss it, but the majority of them do. So that's what you're doing. You're building this interval that the majority of the time, and you're going to be more confident if that interval is wider, that you're capturing your true proportion. So how confident do you want to be? Well, you can really use any percent of confidence level. I think the most common one that I see on the AP exam is to say that you're 95% confident. So let's talk about that one first. And that's because, think about your standard deviations in your normal model, okay? So within one standard deviation, that's going to contain approximately 68% of your data. Within 2 standard deviations, it's approximately 95% of your data. So if I want to be 95% confident that my interval captures, I'm going to go roughly 2 standard deviations above and below my estimate. Okay, but it's not exactly 2 standard deviations. That was just like an approximation that we've been using all year. So let's get a little bit better than that. So if I've got 95%, what's left out? There would be 5% left out. So there would be 2.5% on either tail that's left out. And so what am I going to do? I'm going to do inverse norm. And depending on what model calculator you have, it works a little differently. The TI-84 Plus, the older version, only gives you the left tail. So I'm showing you how to do it with the left tail. If you've got the newer calculators, the CE version, it will do the center. So you could put 0.95 in for your area, and it'll give you the exact interval. But when I put this into my calculator, I got negative 1.96. And it's negative because it's below the mean. So you should recognize that you're going to capture 95% of your data if you go 1.96 standard deviations above and below that mean. So for 95% confident, you're going to go 1.96 standard deviations above and below, and we're going to say standard error because we're going to be calculating this then from our sample statistic. Now, what if you wanted to be 80% confident? Okay, so 80%, definitely going to need to use inverse norm here. That means there's going to be 20% left out, so that would be 10% on each tail, not included. So again, if I do inverse norm and I do for the left area 10% mu and sigma, I get negative 1.28. So I'm going to go up and down 1.28 standard errors, which is like standard deviation, away from my point estimate. So let's go through the whole process now with an example to help you understand this. So suppose you have a huge barrel of craft beads. This barrel is filled with tiny craft beads of all different colors like you see on your screen. You want to know what proportion are red, but you do not want to count every tiny bead in the barrel, so you draw a sample instead. From the barrel, you randomly draw 175 beads and count 28 red in the mix. Create a confidence interval to capture the true proportion of red beads in the barrel. All right, so it doesn't tell us specifically what confidence interval to create. So let's just do a 95% confidence interval. The more confident we are, remember the wider our interval will be. If we are less confident in our interval capturing the true proportion, it's going to be smaller. If you think about it, what's the only way you could be 100% confident that you're capturing the true proportion of red beads in the barrel? You'd have to say, I'm 100% confident that the barrel contains between 0% and 100% red, which tells you absolutely nothing, right? Okay, so as we do this, I'm actually going to use a 4-step process that we're going to continually use in inference, and it's state, plan, do, conclude. So in my stating, I'm just stating what I'm doing along with the parameters. So I'm going to find a 95% confidence interval for P, which is the true proportion of red beads in the barrel, not the sample, but the barrel. Now we're going to plan. In our plan, this is where we check our conditions, okay? And then we state whatever inference test we're using. So I'll tell you what we call this one in a second, but let's identify our condition. So the first condition is that we need a random sample. So I state that you drew a random sample of 175 beads. Now this part in red is not necessary to state, but I want you to remember why we're doing that. And that's so that we can generalize to a greater population and not just make conclusions about our sample itself. That could end up being some sort of AP exam question that's asking you, why are you doing these things? Our second condition is your 10% condition, and I'm stating that the sample of 175 beads is less than 10% of all the beads, I should probably say, in the barrel. And in red, I don't need to say this, but this is for your understanding, and condition is being addressed so that sampling without replacement is okay. And our third condition is our large counts condition, where n times p hat. Notice I'm using p hat, not p, because I don't know the true proportion. So n times p hat and n times 1 minus p hat are both greater than or equal to 10. And I state I've got 28 successes, which are red, and therefore I'd have 147 failures. And in parentheses here, I'm stating why I'm doing that. Again, not necessary, just for your reference now. And I'm doing that so that the sampling distribution of p hat will be approximately normal. Okay, it's like my normal condition. And now I'm going to be able to use my critical value, which I'm going to call z star, to do my calculations. Finally, I name my test. I say that the conditions are met for a 1 proportion z interval. Okay, so this is for proportions, it's an interval, and z, think normal distribution. We're using z star. Now in the do section, this is where I'm going to use do my calculations, excuse me. So I'm going to need p hat, and that is 28 out of 175 beads in my sample is 0.16. Now I'm going to need my standard deviation, but again, I don't have p. I only have p hat. So now I call it standard error. All right, so the standard error of p hat, you can go to your formula sheet and it's labeled there, standard error of a sample statistic, and that's equal to p hat times 1 minus p hat over your sample size. So for our question, this will be the square root of 0.16 times 0.84 over 175, which equals 0.0277. All right, so now that I have these parts, I'm going to build my confidence interval. And if you look on your AP formula sheet, you should see that a confidence interval is equal to your statistic, which is p hat, plus or minus your critical value, which we are going to use z-scores, we call it z star here, times the standard error of your statistic, which again is the next best thing to standard deviation, all right? So now I'm going to fill these values in. So it's 0.16 plus, now for our 95% confidence, I showed you previously how we got that by doing inverse norm. So it is plus or minus 1.96 standard errors away. And what is our standard error? Well, we calculated that to be 0.0277. Okay, remember this part right here is also called your margin of error. So this is going to be 0.16 plus or minus, do that math, 0.0543. So sometimes you'll be asked what's your margin of error, and that's this 0.0543. So what would my interval be? Well, if I take 0.16 and I subtract 0.0543, I get 0.1057, and if I add it on, I get 2.143. So let's interpret what this means. Just noticed as I was interpreting that I have my decimal point in the wrong spot there in my interval. That should be 0.2143 because that's approximately 21%. Okay, so my conclusion, I kind of use this scripted statement. I am 95% confidence in my interval, okay? Remember, my true proportion is not moving around. There is a fixed proportion of red beads in my population. So it's my interval that I have this confidence in. I'm 95% confident that the interval from 0.1057 to 0.2143 captures the true proportion. Now make sure you talk about your population here. The true proportion of red beads in the barrel. And there's barrel spelled wrong. So following this four-step process is definitely going to help you achieve a high score on the AP exam. So conceptually, remember that a higher confidence level is going to widen your interval. Let's go through another quick example, not a four-step process one, but one where we're kind of focusing on interpreting. So margin of errors are definitely used all the time in any polling, especially in an election year when they talk about who's ahead in an election. They always cite a margin of error. All right, so 2 weeks before a presidential election, a polling organization asked a random sample of registered voters the following question. If the presidential election were held today, would you vote for candidate A or candidate B? Based on this poll, the 95% confidence interval for the population proportion who favor candidates is 0.48 to 0.54. Interpret the confidence interval. So my interpretation is that I am 95% confident that the interval from 0.48 to 0.54 captures the, now state your parameter, the true proportion of voters who favor candidate A. What you never want to do is imply that that true parameter proportion is moving around. You could also say I am 95% confident that between 48 and 54% of voters favor candidate A. But the statement you see on your screen is best because you're showing that your confidence is in your interval. In part B, we are asked, what is the point estimate that was used to create the interval, and what is the margin of error? So remember, your point estimate is in the middle, and we're adding and taking away our margin of error on either side to get our interval. So our point estimate, if we're given our interval, is between or halfway between. So how do I get it? Well, halfway between would be find your average, right? Add them together, chop them in half. So my point estimate here is 0.51. And then what would my margin of error be? Well, if I then, remember, so I'm adding and subtracting that margin of error on. Okay, so if 0.54 is the upper end of my interval, if I just do 0.54 minus 0.51, my margin of error is 0.03. And then part C, based on this poll, a political reporter claims that the majority of registered voters favor candidate A. use the confidence interval to evaluate this claim. So when I look at this interval, think about majority. Majority is more than 50%, and this interval includes values less than 50%. So because there are plausible values of p, or true proportion, less than or equal to 0.50 in the confidence interval, the interval does not give convincing evidence that a majority, which I'm stating is more than 50%, of my population of registered voters favor candidate A. The last thing I want you to do in this is consider how to interpret a confidence level, which is easily confused with interpreting your confidence interval, okay? So you should always interpret your confidence interval in a problem, but once in a while, you're asked to explain what do you mean by your confidence level by stating a 95% confidence level or a 90% or an 80%. What do you mean by that? So here's a general statement, and it means if we were to select many random samples from a population and we constructed a confidence interval using each sample, about C% of the intervals would capture the, and then you state your true parameter in context. So in this particular one, so I'm stating that if we were to select many random samples of registered voters, so you don't just do it one time, and construct a 95% confidence interval using each of these samples, about 95% of our intervals would capture the true proportion of all registered voters who favor candidate A in the election. Okay, so I'm talking about my confidence level. If we were doing a 90%, you would just state if we were to do this many, many times, select many random samples of registered voters and construct a 90% confidence level using each sample, about 90% of these intervals would capture the true proportion of registered voters who favor candidate A in the election. So if it's a 90%, 10% of the time you're missing it. So 95% confidence, 5% of the time you're missing that true proportion.